the question, this is the question. Given two ordered arrays, how to merge them to get an ordered array containing the elements from both ordered arrays. You can see, if you still remember the last three questions of our part C of the midterm, you can see related to the merge question, right? Yeah, two ordered arrays, right? But the last one is not completely two ordered because they're x5. x5 is a separated element. Other than x5, they're two ordered arrays, right? Yeah. All right. How to solve this simple, but a very basic question. How to achieve balanced subarrays? Yeah? Because when we distribute, so here, when we have a chance to distribute our data, we want to do the evenly split. Yeah. We want to do, evenly split. Yeah. All right. So the idea, whenever we merge two subarrays, we want to make of equal size. Yeah. In the merge sort, because divide and conquer, merge sort, you apply divide and conquer. So there is a divide step, there is a conquer step. But the divide step, you have freedom to choose how to divide, right? But when you choose how to divide, you want to split the two data, two subarrays, evenly split. Let me use this line segment to represent the original array. Divide and conquer. When we divide, we split in the middle, as even as possible. It's possible one subarray has one more element than the other one. So that's okay. Almost the same size. Split in the middle. The first round. Then conquer, we do the recursive function call. Recursive function call. But when you do the recursive function call, so you treat each subarray as the original array. Then you do the same thing again. Each subarray. Then you do divide and conquer. Right? Each subarray, you do another round divide and conquer. But when you do the second round, you still split in the middle of the current subarray. And keep doing things again and again. And you need to stop somewhere, right? At some point, you cannot split anymore. Because each subarray, there is only one element. How can you split one element? So the last step, each subarray contains one element. Then you have to stop. After that, you merge two adjacent subarrays. Two adjacent subarrays. We apply the solution. So here we assume. We can find that solution easily. Okay. We will look at that solution later. But if we can solve this problem number 14, then we merge two adjacent subarrays, apply that solution. So after the merge, each subfile becomes ordered file, right? Ordered. Another round merge, second round merge. So larger ordered subarrays. Then we'll keep doing the merge operations round by round. Next round, then the last round. So after this round, we only have two ordered subarrays. The last round, we merge these two ordered subarrays, we get one whole ordered array. That's simple. So So that's the merge sort. So here you can see, if we can solve this problem number 14, we have the solution, divide and conquer, recursion. Recursive function calls, we have the whole merge sort. All right. Yeah. But this, if you apply this method, so one thing you can get, here we hope, but actually we have good chance to get it, avoid poor worst case performance. Why we have a good chance to avoid poor worst case performance? Because we do evenly with even split. We do even split by our balancing principle. We will not have, we can avoid the poor worst case. Because the worst case usually occur at the extremal cases. Extremal. So one so far very small, and the other one very large. The extremal case usually corresponds to the worst case. But here we never have the extremal cases. So we will not have the bad worst case. We always have worst case, right? But the worst case is not that bad. Okay. All right. So this is main property of this merge sort. Its worst case is not bad. Its worst case is not bad. Here you may ask me, what do you mean bad or not bad, right? Here I use the formula to give you an idea. So what kind of formula we treat as a bad one? Okay, bad worst case. What kind of formula we do not treat as a bad worst case? Okay, all right. So when we talk about the worst case, the previous three sorts, selection, bubble, insertion, the worst case, big theta of n squared, right? So if your worst case has this kind of efficiency, we treat it's a bad worst case. Bad. N squared is very bad, right? Slow. All right. Then, if your worst case better than that, n log n. Not bad. Not bad. Okay. So our merge sort, we will have this case. Our merge sort. Okay. Later you will see. After merge sort, quick sort. After merge sort, we will learn quick sort. Quick sort, also this bad case, worst case. Because quick sort cannot avoid extremal cases. Quick sort, what do we do? Do it based on the procedure, the process. We cannot avoid extremal cases. Then we cannot avoid this kind of bad worst case. Merge sort, we can avoid the extremal cases. We always split in the middle, so we avoid the extremal cases. So then we won't have the bad n squared, worst case, n squared worst case. All right, so let's look at solution, merge solution. Let me use the diagram. Order A subarray ordered, B subarray ordered. How to merge these two ordered subarrays. Based on our intuition, actually, some of the students already apply this merge operation in your part C. I saw. Several. Actually, your idea is the merge idea. at least 2 or 3 students, at least, already apply this merge idea. Yeah. All right, very simple. Yeah. All right. Every time we start from the smallest elements in both arrays, yeah. When we start, we do one comparison. When you do one comparison, you can see after your comparison, you can put one element in place. Yeah. Yeah. Because both arrays are ordered, and when you select the 2 smallest elements in 2 ordered array, when you compare these 2 smallest elements in these 2 ordered arrays, the smaller one is the smallest in your whole data, right? In your whole data. Yeah. The smallest in the whole data, that means it is in place. So you can put it in place. One comparison, you can put one element in place. Yeah. So here, let's use the minimum. And min 0 represent the smaller one in the first comparison. Yeah. Max 0 we represent the larger one in the first comparison. Yeah. Then this is our destination array. So we want to put the elements in place in our destination array. Yeah. So after the first comparison, we can first put min 0 in our destination array. One comparison, we put the min 0 destination array. Right? All right? Yeah. After it, because max 0 still, we don't know the position of max 0, right? We don't know still. We need more comparison, another comparison. So our next comparison, yeah, so here we assume max 0, yeah, yeah, winner in this B subarray. So next comparison, we should compare max 0 with the next element in the A array, A1. And the smaller one of these 2 elements, let us use min 1. Okay. Min 1, the smaller one of A1 and B0. After the second comparison, we can put it in place. Yeah. The second location in our destination array. Yeah. In place. Here you can see every time you only need to do one comparison, you can put one element in place. Another round, you put another element in place. Now you think about our question number 3 in part C. We have 2 ordering, each one 3 elements, right? But we need to find the third smallest. The first comparison will find the smallest. Second comparison will find the second smallest. Third comparison, third smallest. You need a 3 comparison. Yeah. Just like this. Min 0, min 1, min 2. That's your third smallest. Yeah, you're done. Yeah. Yeah. Some students use this way. Yeah. Some students use this way. So very simple solution. Yeah. Okay. Yeah. If you use this way, yeah, very easy. Yeah. Yeah. But definitely you have many other ways. Yeah. Many other ways. Yeah. You can get the same solution. Yeah. But many students give me 4 solutions. Yeah. 4 solutions. The reason, yeah, I look at the student, later I will talk about. But I can tell you the reason. So those students, yes, so many students, when they do comparisons, they do not do this way, okay? They do this way. All those students who give me 4 comparisons, they do this way. Okay? Yeah. This way. You do more work. This way. You do more work. Yeah. Not the best way. Yeah. Yeah. All right. So, yeah, because you do this opposite direction, right? Opposite direction. The largest in one array, the smallest in the second array. The best case, one comparison that you get best case. But we want to do the worst case. Okay. Then, the worst case, you cannot use 3 comparisons to do it this way. Okay? Yeah. All right. Yeah, so in this way, you can see every time we put one element in place. Yeah. But the end, so we want to see the last step, the last comparison. Okay? Put the last element in place. Yeah. Second to last, actually. Second to last. Because the last one, you only have one element left, no comparison needed. Right? One element left, you drop it in place immediately without any comparison. So you can save one comparison for the last element. Yeah. Yeah. So any location before the last element, you need a one comparison. Okay? Any location before this last element, you need a one comparison. Then you can count how many total number of comparisons. But it's for the worst case, not for the best case. It's for the worst case. Yeah. All right. Yeah. Yeah. So here we look at the worst case. Yeah. For every new min added, we may need a one comparison, because if you do not get the worst case, you can do better, right? Yeah. You can do better. Yeah. So later we will see. We can do better. Yeah. We can stop earlier than we reach, second to last position. Yeah. Because much earlier we already put the elements in place. Okay. The remaining elements, we know they should be in place. We know. All right. So here, this is worst case. Number of comparisons for the worst case, 2k minus 1. So here we assume the size of each subarray k, size k, 2k, that's the total number of elements in these two subarrays, but we need to minus 1 because the last one we do not count. So 2k minus 1. Yeah. And in this merge step, here you can see we apply this merge step on two subarrays with equal size. Equal size. But you can imagine, you can easily generalize, not necessary two subarrays with equal sizes, right? With equal size, not necessary. The two arrays with unequal sizes, we can do the same way, right? Yeah. Two ordered subarrays with unequal sizes, we can still do the same thing. Yeah, yeah. So the same method still works. Yeah. All right. So this time we do the merge for the worst case, for the general merge step. This time, the size of the first array, m size. The size of the second ordered array, n size. M and n. We do not require these two numbers the same. Yeah. So we still, idea is the same. Yeah. Every comparison, we put one element in place in our destination array. Yeah. Yeah. Second to last, our worst case, we do one comparison for the second to last element. Yeah. Yeah. So in that case, the total number of comparisons should be the sum of the number of elements in two subarrays minus 1. Because the last position, we do not need to do any comparison. Yeah. So the answer, m plus n minus 1 for the merge step. M plus n minus 1. That's worst case. Not best case. Yeah. But next we need to look at the best case. All right. Yeah. This formula. Okay. Yeah. The worst case formula, best case formula. Yeah. Two different formulas. Right. Let's look at the best case. This time, best case. Yeah. We still look at the general case. Yeah. All right. Now think about how can we get the best case? Under what special situation we do the minimum number of comparisons? That's the best case. For what kind of data? Yeah. We use the same idea, but our data has the special property. Yeah. Based on the special property of our data, then we only need to do the minimum number of comparisons. That's the best case. Yeah. Can you imagine what is the special data property we should expect to get the minimum number of comparisons? What's that? Yeah. The goal, minimum number of comparisons. Yeah. That means we should stop some point earlier. Yeah. So now reach the second to last position. The earlier the better, right? Yeah. At some point, because the remaining, we do not need to do any comparisons. The remaining part, because we know the remaining elements should fall into those locations automatically without comparisons. How to get that?
If the smallest element in one of the arrays is larger than it's larger than the largest element in the other array, then we only have to compare the first array against one element from the second.
Yeah. All right.
And then all the other elements are in place.
Yeah, all right, yeah. Good comment, yeah, but here I need to explain a few things. Yeah, good comment, good observation, yeah. But I want to split your comment into two halves, because there are two important questions we need to address. First question, all right. He mentioned did you talk about one shorter array, one larger array?
No.
Small? Oh, you didn't? Okay. Yeah. Because we need to be aware of one array is shorter than the other. Okay? Yeah. All right. So here the idea. Yeah. But your question mainly, the second question I want to explain. Yeah. The first question. Yeah. Because here you can see every comparison, one element beats another one, right? One element beats another one. Okay, the loser should be placed, so put in place the loser. Okay, yeah. All right. If we use this way, all right. Two fighters from two different groups, right? Two different groups. Okay, yeah. All right. How to arrange? Yeah, under what situation the number of fights is the minimum. Number of fights is minimum. Okay? All right. So you can imagine the first fighter in one group beats all the fighters in the other group. How about that? The first one already get the job done. The remaining fighters, they do not need to do anything, right? They can be put in place automatically. Okay? Yeah. Yeah. So the first one in one of the two teams just beat all the players in the other team all the way from beginning to end. After that, because we know the remaining elements are greater than the first one, they can be dropped into place automatically. That's the best case. Yeah. But for that best case, we want the first element in the longer subarray to beat all the elements in the shorter subarray. Then we only need to do the number comparisons the same number as the number of elements in the shorter subarray. That's the best case. Okay? Yeah, that's the first question. The best case. Yeah. the special data, okay? Yeah. Like that. All right. Strategy. Try to exhaust one of the two arrays as early as possible. Yeah. Yeah, but we want to exhaust the shorter array. Okay? Yeah. Yeah. All right. So the best case, the minimum of m and n. Yeah. Minimum of m and n. Smaller number of m and n. Yeah. Yeah. That number comparisons, the formula. Yeah. The first question. Second one, yeah. So Matthew talked about another idea. Yeah. So this idea, yeah, many students tend to use that idea, yeah, in our homework questions. Yeah. Homework questions, I may give you several best case, worst case questions, several. Yeah. But when I did grading before, many students use the idea Matthew just mentioned, yeah, to get the best case. Okay, Matthew, yeah, that best case, you just do one comparison, you get it, right? Yeah. So, yeah, Matthew, in his description, he assumes 0, when 0 greater than am minus 1, but he compare b0 and am minus 1 as the first comparison. That's the best case. That just one, right? Not this number. Okay, all right. Now I want to explain. Yeah. Now I want to explain. Yeah. Yeah. So we do this way. We call here what we are doing is the standard merge operation. What we are doing? So we always compare the smallest with smallest. That's the standard merge operation. Okay, standard. Smallest compare with the smallest. All right. Yeah. The idea Matthew talked about, so it's not standard, yeah, a special way, very special way. Okay, yeah. But in that special data, you just talk about the special data with this probability. That your best case is much better, yeah, because only one comparison. Your best case is much better, all right. But when we select an algorithm, yeah, because the best case usually is less important than the average case. The best case, because the percentage of the best case is so small. Yeah. The average case more important. Yeah, percentage, average. The average case, more important. Yeah. So so our goal, don't want to look for the best, so the best case, that's not our goal. Okay, so we want the best overall efficiency. Okay, yeah, all right, yeah. So in that way, our standard merge operation is better than this special case. Yeah. Why? Part C, question number 3, give us some idea. Part C, that one, because many students, they do comparison this way. They compare this. You can get the best case, right? One comparison, you can get the best case. But that's not our goal, right? Yeah, because we want to get the best worst case. So in this way, your sacrifice. So you sacrifice a better worst case. Because in the result, you get a full comparison for your worst case. Yeah. All right? So you sacrifice in other cases. Yeah, not just worst case, general case. So, all right? Yeah? Not worth it. Okay? Not worth it. Because we want, better overall. Better worst case, better overall cases, we want that. We don't want best case. We don't want the best case. Okay, so that's the main point. That's the main point. Yeah. All right. Yeah. Yeah. So our part C, midterm questions. Yeah. So we can see something. Yeah. Some from that special question, we can see this. If you do it this way, your overall pop-ups will be slower. Will be slower. Your sacrifice is much larger than your gain. Okay, your gain very small. Okay, yeah. That's the point. Okay, all right. So now we finish the worst case sort. Okay, yeah. We finish the merge operation. Yeah. So the general best case, general worst case, we have both. Okay. Then C.3 efficiency analysis for the merge sort. We want to do some efficiency analysis. Yeah. All right. Derive recurrence relation. Yeah. We need to do some formula calculation here. Yeah. All right. Estimate worst case efficiency. Yeah. Because the goal, we want to prove the worst case is big theta of n log n. That's the worst case. How to see that? How to see that? We use the estimation way. Yeah. Estimation way. Yeah. The computer science estimation. Yeah. Not the rigorous math. Rigorous, very complicated. Too complicated. Yeah. But when we use our CS estimation way, yeah, much simpler. Much simpler. But we can see this kind of approximation easily. Yeah. All right. Yeah. Original array like this. All right. So we assume the number of comparisons to sort this array by the merge sort is capital T function, T of n. Yeah. Divide and conquer. Yeah. When we do the divide and conquer, we split, the two subarrays, both half of the original data size. Yeah. All right. We'll make even split. Yeah. All right. The size of each one, n over 2, approximately n over 2. Yeah. Yeah. So here we do not use the, very accurate representation, floor function, ceiling function, the accurate way, right? Accurate mathematics, but because if we don't want to go rigorous math way too hard to do the calculation. But we do approximation, yeah, because this number very close to the accurate number, right? So close. So we don't worry about the small difference. Yeah. Yeah. All right. Yeah. So two subproblems, T of n over 2, but we need to do twice. Twice. That's the cost. Twice. But there is another cost. Other than we conquer step. Yeah, we call recursive function conquer step. Second conquer step. After that, we need to merge these two ordered arrays. They become ordered arrays. Combine them, merge them. We need to pay another type of cost, merge cost, combine cost. Yeah. That cost, yeah. Here we use the worst case. Worst case, n minus 1, right? Yeah. N minus 1, can we use n to approximate n minus 1? One difference, because here we do approximation, right? Approximation, we drop -1, not a big deal, okay? Yeah, very close. So we are very satisfied if the difference is very small. We control this difference very small. Then we have no problem. Yeah. Okay? Yeah. All right. So this is the recurrence relation we derived. Yeah. T of 1, 0. T of 2 equals 1. Yeah. Oh, yeah, sorry. T of 1, 0. T of 2, 1. 1 comparison. Then, recurrence relation. Yeah. Yeah. All right. The question, how to estimate this capital T function? How to estimate this capital T function? Use the approximation way. Yeah. All right. All right. Now, consider simpler case. Power n is power of 2. That's it. That's the simplest we can imagine, right? N is power of 2. Because when you do division by 2, you always get nice integers. So you never have non-integer numbers. N is power of 2. Yeah. So let us plug in n power of 2 and see what's the estimation result. All right. Yeah, so plug in. Yeah, we get a new form of the equation. Yeah. So division all gone, right? Division all gone. Okay? Yeah. Yeah. But the question, how do we solve this new recurrence relation? Yeah. A lot of power of 2 here. A lot of power of 2. Yeah. How do we handle these power of 2 structures? Yeah. 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 All right. Yeah. So there is a commonly used method here. Yeah. Division method. Division method. Power division by power of 2. Division method. Okay? Yeah. So when we apply the division method, yeah, we divide it by 2 to the k, both sides. So left hand side, t of 2 to the k over 2 to the k. Yeah. Yeah. So here, what's the benefit of this division method? Because after you do this kind of transformation, you can see when you compare the structure at the left-hand side, structure at the right-hand side, similar structure, right? Yeah. The nice thing of this transformation is because you discover some special structure repeated recursively. Yeah. That structure, okay, that fraction, special fraction structure, repeated left-hand side, right-hand side, recursively. Okay, all right. So our way, when we see this, we introduce a new function represent. We define a new function represent that fractional structure. Yeah. So let us introduce a new function called the g function. G of k equals this t to the 2 to the k's over 2 to the k's. Because after this new function introduced, we can make the previous equation much simpler. Simpler. Yeah. Yeah. No fractional structure anymore. Yeah. All right, let's look at this slide. Substitution. After the substitution, yeah, this g function, yeah, we get a new equation. G of k equals g of k minus 1 plus 1. Yeah. Much simpler, right? Yeah. This new, you can see, yeah, comparing with this previous recurrence relation. The new one much simpler. With this simpler version of recurrence, can you find a solution quickly? Yeah. We just want to solve this new recurrence relation. Yeah. Although we need to fix the initial conditions. What is the initial condition of this g function? Yeah. We need to figure out. G of 1, you plug in 1. Okay. G of 1, that's t of 2 over 2. T of 2 is 1. over 2, 1/2. G of 1 is 1/2. Okay, all right. Look, how do you find the solution? Yeah. 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 Because you can do iteration another round. So it is G of k minus 2 plus 2. Another round. Yeah. Keep doing round by round. Yeah. What is the last round? Yeah. You need to see the last round. Last round, this column should be at G of 1, right? Yeah, because G of 1 is the initial value. Yeah. So the last round, yeah, G of 1, but what is the number here? You need to figure out the number here. So here, remember, we learned invariant concept. Invariant. So what is the invariance property here? The sum of these two numbers. Size number, constant number. Size n minus 1 plus that constant, yeah, the sum is k. This row, n minus 2 plus 2, also k. So after we find this property, we can keep track of our data. Okay? Yeah. Because here, dot, 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 how to keep track of all the equations, right? We get lost. Yeah. But if you can discover this invariance property, then you won't get lost. Yeah. Because in our last row, the sum of this 1 and this constant number should be k. So that constant should be k minus 1. Yeah, k minus 1. Okay, all right. There. Because G of 1, we know 1/2. Okay, 1/2. Yeah. Yeah. K minus 1 plus 1/2. K minus 1/2. So this G function is k minus 1/2. G function. We find the G function. Then we go back to the definition of the G function. Definition of G function. Okay? All right. So T of 2 to the k over 2 to the k equals k minus 1/2. So T of 2 to the k equals parenthesis k minus 1/2 times 2 to the k. Yeah. Yeah. All right. Yeah. Yeah. But we need to go back to n. We need to go back to n. Yeah. N equals 2 to the k. Yeah. Okay. T of n, yeah, k equals the log base 2 of n. Okay. Yeah. So T of n approximately this 1/2 we can drop, right? Yeah. Yeah. No big deal. Yeah. Yeah. Small loss, but we can simplify a lot. Okay. Yeah. Little k, we use not natural, log base 2. Yeah. LG in computer science, that's log base 2. Okay, all right. LG of n times 2 to the k, that's n. Okay. So here you can see with this special type of n, special, n equals the power of 2, we can get this approximation. N log n. N log n. Yeah. But that's for special n, power of 2n. Not for general n. Not for general n. Yeah. So this, the calculation we're doing here, yeah, for special n, power of 2n. Yeah. Can we make a reasonable guess? For the general n, we still have n log n as a guess, reasonable guess. Yeah. When we make a guess, we need to base on some evidence, right? Clue, something like that. Yeah. Okay. Yeah. So that's something. Yeah. And not a. You just guess, baseless guess, right? It's not a baseless guess. Okay, yeah. All right. Yeah, but next, let me me see how much time I have. Yeah, okay, yeah, still have some time, yeah. All right. Yeah. Yeah. But the next, yeah, I want to do one thing. Yeah. The first thing I want to show you how to estimate for the general case. How to estimate for the general case, yeah, using some relatively simple way. All right. Let me do here. Yeah. All right. This is our recurrence relation. Now, this time we do estimation. Yeah. We use a special way. Yeah. They call it draw recursion tree. Yeah. All right. So here we draw recursion tree. Okay, draw a recursion tree. What's that? All right. We start. When we start from T of n. T of n. So that's our root node. We draw a tree, binary tree. Yeah. Binary tree. How do we get this T of n function? We apply this recurrence relation. The right hand side. Okay. Left hand side function T of n we put as a root node. Yeah. Right hand side we do some special interpretation of the right hand side. All right. The right hand side two branches. Yeah, because here the coefficient 2. Yeah, so we should have two branches. Okay, all right. The left child node, yeah. So here, when we, all right, the left child node, T of n over 2, yeah, T of n over 2, all right, yeah. Yeah. But in this level, other than the t terms, then there is a non-recursion term, that n. Yeah. So we need to accumulate all the non-recursion terms. Accumulate. Okay, all right. Then another round split. What's that? Another round split. Okay. Yeah. All right. So T of n over 4, T of n over 4, but there is a non-recursion cost, right? We need to store n over 2. N over 2. Yeah. Okay? Yeah. All right. Here, the same thing. Yeah. N over. Sorry, 4, right? Yeah, not 2. Yeah. The size. And non-recursion cost n over 2. But let's accumulate this level. The total non-recursion cost, is it n? Still n? Yeah. Still n. Okay? Can we go to another level, going down, split? Going down. Okay, split. All the way to the bottom. Can we do that? All the way to the bottom. To do split like that. That is our recursion tree. Okay? Can you see each level, the total non-recursion cost always n? Always n. Okay? All right. But at the bottom, yeah, the end should be T of 1, right? Yeah. So when you stop, when you reach the bottom level, all the T of 1, you stop, right? Yeah. But non-recursion cost should be F, right? Yeah. So here the question, how many levels do you have? So you do, every time you do division by 2, so when do you reach the bottom? Approximately 1, reach the bottom. Is it approximately log of n? Approximately. Yeah. Approximately. Log of n. Yeah. Right? Because here, you do division by 2, although your n may not be the power of 2, right? Yeah. But the question is, can you find the 2 adjacent power of 2 to put the n between 2 adjacent power of 2? Can you do that? Given any positive integer n, can you find the 2 adjacent power of 2 such that n is in between these two numbers? Yes, right? Yeah, obvious. Yeah. Yes. When that happens, do you have k less than or equal to log base 2 of n less than k plus 1? Right? Yeah. Now, you use log to approximate k. Is it a good approximation? Because difference is less than 1. When you use log base 2 of n to approximate k, the difference is less than 1. So it should be a good approximation. Yeah. Now we can use that. You have this many levels, log base 2 of n levels, and the non-recursion cost from each level n. So total, is it n log n? Right? The total accumulated cost. N log n. So this method, recursion tree method. Although it's not a rigorous math, but you know, a good approximation. Yeah. Yeah. All right. Yeah. So that's the, you know, this way. So you can see, we get the worst case efficiency, not worst case. Worst case efficiency. Okay. Yeah. All right. Yeah. Then, yeah, let me use a few minutes to talk about our part C questions. Yeah. Number 3, yeah, I already explained number 3, right? Yeah. Yeah. Number 4, very closely related to number 3, right? Yeah. Because after one comparison, yeah, so here, let me talk about a little bit. Number 4, question number 4. Yeah. Because question number 4, yeah, yeah. A1, A2, A3, A4, A5, A6, B1, B2, B3, B4, B5. Okay? Yeah. Yeah. And it's given, you know, A3 less than B3. Yeah. So after elimination, we get question number 3. Okay? Because yeah, many students, they didn't do right at the elimination step. Elimination. Okay? Elimination telling us A1, A2, A3, all the elements in this set less than A4, A5, A6, and B3, B4, and B5. Okay. Yeah. First, we can see that. Okay. Each element. Yeah. first set less than each element in the second set. All right. There are 6 elements in the second set. So that means these elements less than at least 6 elements, right? At least 6 elements. Then it cannot be the median, right? Yeah. So the median cannot belong to these 3 elements. Yeah. Cannot belong to. All right? All right. But another, yeah. Actually, this part, many students can get this part, but the other B4, B5, there, many students couldn't see this. Yeah. These elements greater than, so B1, B2, B3, A1, A2, A3. Yeah. Many students cannot see this one. Yeah. If you can see that one, the median cannot belong to these, 2 elements. It cannot be. So these 5 could be removed, eliminated. Yeah. But after elimination, what's left? Yeah. So after elimination, you get to the previous question, right? You get to the previous question. Okay, all right. The previous question. So the first ordered array, second ordered array, B3. Yeah. And you need to find third smallest, right? Yeah, because the median becomes the third smallest. Original median becomes third smallest. Is it the same thing as the question not 3, Q3? Same question, Q3. 2 ordered array, each one 3 elements. Yeah. 2 ordered. Then when you compare, from the lower end, do comparisons from merge. But when you do the merge, you do not do complete merge. Yeah, some students I saw, or a small number, some students, they connect to the merge operation. That's good. But the merge operation, they complete that merge. Then you do too much. Because here we need to stop. As soon as we find the third smallest, we stop. Okay? You do not need to do anything after third smallest. Because we get a solution. Yeah. Stop immediately after you get third smallest element. Yeah. Yeah. So that's question 4. So question number 5. Yeah. Question number 5. Here, I want to talk about the step closely related to our merge operation. Yeah. Closely related to our merge operation. Yeah, we just learned the merge operation. Yeah. All right. Yeah. If I use diagram, so question number 5. If I use diagram, so I draw like this. 4 elements ordered array, x4, 3, 2, x1. 4 element ordered array, x9, x8, x7, x6. Yeah. So many students gave me this way. The first comparison. Yeah. First comparison did like that. Because this way corresponds to the best case. Yeah. one comparison. For the best case, yeah, that's the best. Okay? Yeah. Yeah. But our goal, we want to get the best, the worst case, not the best case. Okay? Yeah. All right. So this way is not good for the worst case. It's not good for the worst case. All right. So this is the, most popular solution, most popular. Yeah. All right. Then a few students, yeah. So they did merge way. They did a merge way. A few students did a merge way. Yeah. Oh, some students did partial merge way, not the full merge way. Partial because tournament. Yeah, several students they did a tournament comparison, full comparison like that. Okay. Yeah, several students they did tournament method. Yeah, yeah. But so many students they didn't do discussion. After tournament method, you need to do some discussion, telling me more information. No. Many students just put there. Okay? Yeah, put there. Yeah. All right. Yeah. Now, let's look at the merge way. Yeah. Not tournament way, merge way. All right. Merge way. Yeah. Now we feel more comfortable. But at that time, at the test time, if you can connect to the merge way, that's, really something very good. Yeah. Yeah. So all right. So the merge way, our first comparison, x1 and x6, that's the first comparison. So you can get the smallest element among these 8, because remember there is a x5 there, okay? You cannot say you put an element in place, right? Because still there is x5 there. Okay, yeah, but let me draw our destination. All right. So first comparison, we get the first element, smallest element in that 8 elements subarray. Okay, 8 elements. Yeah. So x5 we need to work on it later. Okay. Yeah. Work on it later. Then second comparison, could be this way, could be that way. Yeah. Based on our merge operation. Yeah. One more comparison. You put a second. Okay. All right. Yeah. Then third. Could be that, could be, yeah. So, yeah. Third. Okay, all right, yeah. All right. Fourth comparison, yeah. 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 So, the idea. Fourth. 4 comparisons. Yeah. Yeah. But we are very close to the median, right? We're very close to the median. Okay, all right. Yeah. But let's assume so after 4 comparison, so let's do some cleanup work, analysis, a little bit cleanup work. Okay, all right. Yeah. Let's consider what is the candidate for the 5th overall smallest. The candidate. So here, let's think about the candidates. X5 should be the candidate, right? Yeah. So X5 should be the candidate. Sorry, X5. All right. So let's assume here, yeah. Because X3 is the current, the pending one, right? Yeah, X3, yeah. Because if we keep our merge operation, the 5th one, yeah, because we should compare these two, right? Yeah, the fifth one. So these two, actually, they should also be the candidate. Yeah, yeah, because yeah, x3, yeah, x8, candidate. Okay, candidate. All right. Yeah. Now, x5. Let us compare x5 with the fourth smallest, and let's see what happened. Okay, yeah. So only you have two cases: x5 less than x4, and x5 greater than x4. Right? When x5 less than x4, can you get a solution immediately? x5 less than x4. Yeah. x5 less than, is it this fourth element is the median? Because the fourth element greater than 4, right? Including x5 and 4. And this fourth less than the remaining 4 elements. Yeah. So this is the best case. Okay. Best case for this algorithm. Okay. It's not the best case overall. Okay. Because when we talk about best case, yeah, sometimes we say best case for this particular algorithm, yeah, but not overall best case. Yeah. Oh, so best case for this algorithm. All right. We don't look at the best case. Yeah. So we do not assume this. Okay. Yeah. We're targeting worst case. So we should assume this condition. So we should assume x5 greater than x4, then x5 is the candidate, right? Yeah, because greater than x4. Yeah. x3 greater than x4, x8 greater than, and immediate in the current order. So there are elements immediate in current order. Yeah. So do you think the smallest, the minimum of the three should be the fifth of the three? Should be the minimum of the three. How about that? So the three candidates, okay? Three candidates, but in these three candidates, minimum of them is qualified for the median. Yeah. Okay, all right. Yeah. So I want to complete. 2 minutes. Yeah. Use 1 minute to complete. All right. x5, x4, is this the comparison number 5? Because they already used the four comparisons. That's comparison. Find the minimum. Do you need two more? Two more comparison? Two more? Yeah. Adding together 5, 2 more. So in this method, you need 7 comparisons. Yeah. That's not the best solution. Best solution is 6 comparisons. Yeah. But this tells us close to the best. Close to the best. Okay? So by the merge operation, you can get a solution close to the best. Yeah, but not the best. Best still much more sophisticated, much more complicated. 6 comparisons, but much harder than this one. Yeah, but it's a second to best solution. Okay, a merge way, second to best solution. Okay, a second best solution. All right. Yeah, let you go. Yeah. So we complete the merge sort. Yeah, next time quick sort. Quick sort.